Welcome back. This is the second recording of this section, I believe 3D, or talk about vector spaces and then what we mean the linear map is invertible, and then now we're going to use that to define what we mean two vector spaces are isomorphic. And then we're going to, once we know that definition, then we're going to use that to actually study for a linear map from a finite dimensional vector space V to a finite dimensional vector space W, or then what can we say about all those LVW, right? That is itself is a vector space. All right, so that's the main goal for this section. So let's look at the first definition, or in this second recording. All right, so we said, well, two vector spaces are called isomorphic if there is an invertible linear map from one vector space onto the other one. Right. So it does not matter which one is from V to W or W to V, right? Because we know if there is a linear map which is invertible, then the inverse is also invertible. Or if T is from V to W, the T inverse is from W to V, right? So either way is fine. So this kind of like some kind of a symmetric relationship here, right? So we don't really care where to where, right? As long as there is one from one to the other onto the other, then that is these two vector spaces are called isomorphic. All right. So let's make an example here to kind of have a better understanding on the definition, right? So we've been talking about the R3 are really for something easy for everyone to understand, but we also talked about the polynomial space, vector space. For instance, let's put the P sub 2 of R. These are the polynomials over the real numbers, and the degree less than or equal to 2. All right. So we use this notation, means these two vector spaces are isomorphic. Right. And then why is that, right? So then you need to be able to find the invertible map which go from either R3 to P sub 2 of R or vice versa, but there need to be one, right? But the way to think about that is not very hard because we know the R3, there are three vectors in any basis. So if we take the standard basis, then that's going to be let's say 1, 0, 0, right? 0, 1, 0, and then 0, 0, 1. Right? And then what is this is the basis of R3, right? So what is the basis of P sub 2 of R? Well, these are the polynomials degree less than or equal to 2. So we can put 1 here, and then we can put x here, and then we can put x squared here. Right? So then, well, then this correspondence, three bases are to other three bases. We know by our discussion earlier, I think in section 3C, we talked about matrices. We said, well, if you define how to make because each linear map is uniquely determined by how this map works between the bases, right? And then that can be actually represented by a matrix. I remember that. And then, so if we make this correspondence, say the first one here, 1, 0, 0 corresponds to 1, 0, 1, 0 corresponds to x, and the 0, 0, 1 corresponds to x squared, then you can check this is actually a linear map, and then that is invertible, or because first this is unique, right? So everything here, if you have something like a 3 to 5, right? So then this give you a 3 plus 2x plus 5x squared, right? So obviously, if you have two different vectors in R3, that can go to two different polynomials. Or the other way to think about this, if you have the two polynomials the same, then by this construction, of course, their original vectors in R3 is the same. All right, so that's the injective, and then the surjective can be done by, well, any polynomial in P sub 2 of R, there must be a linear term, there must be a constant term, a linear term, a quadratic term. Those coefficients go back to give you the R3, right? So this kind of correspondence is actually invertible, or either from R3 to P sub 2 of R or vice versa. So these two spaces So you can think, well, they are totally different objects, right? One is the collection of all those vectors in R3, in a three-dimensional, regular three-dimensional Cartesian space. The other is the polynomials, but really, besides the name or the way you write them, well, then there's not much difference, right? When you add two vectors, that means you add these two corresponding polynomials. When you multiply a vector by 10, that means you multiply that polynomial by 10. All right? So then all those except the names, all the other properties, you'll always be able to find the counterparts. So then that's something we call these two vector spaces. They are isomorphic. All right, so this is the example. And why we want to know this? Well, because the next theorem tells us two finite dimensional vector spaces these are isomorphic. Again, this is a if and only if statement, or if and only if they have the same dimension. That's actually the example we made belonging to this case, right? So both have the dimension of 3, all right? So then they should be isomorphic. And let's prove this. All right? Then this is going to tell us actually we can basically, in some sense, you can basically just classify all the finite dimensional vector spaces by their dimensions, right? Because all the things dimension are 3, well, then they are isomorphic to each other, right? If you have a thorough understanding on one of them, then you have the same understanding on all others with the same dimension. All right, so this is a very powerful, strong statement here, help us to have a much deeper understanding about the vector spaces, at least the finite dimensional case. So what we're going to prove here is, well, two things, right? If you are assuming they are the two vector spaces are isomorphic, in other words, there's an invertible map between them, all right, then we're trying to show they have the same dimension. Or if you show they have the same dimension, then you're trying to show there is a map between them, all right, invertible map between them. So let's suppose our V and W are two finite dimensional vector spaces, right? Two finite vector spaces, all right, and the dimension of V is equal to the dimension. Well, let's first prove that there and V and W are isomorphic. That will be relatively easier direction when you do the other one. Are isomorphic. Maybe let me put it this way. Let's state this, and then now let's prove the one direction is suppose our V and W are isomorphic. All right. So then consider by the definition there exists an invertible linear map T from V onto W. That's just our definition, what we just defined this a minute ago, or what we mean the two vector spaces isomorphic. All right. Then let's consider that fundamental theorem of linear map. All right, remember this one says what? Says if you have a linear map from V to W and V needs to be finite dimensional, then the dimension of this V is equal to are very familiar with this theorem, or we have used this before, or we're going to use this now. Or so this is a very powerful theorem here. said what is the dimension of V, right? It's the dimension of the nor T, and then plus the dimension of the range of T. All right. So that is something we talked earlier. Let me. All right. So we have this very important theorem here. It's on the page, I think 63 of the textbook. Okay, that is a 322 fundamental theorem of linear map. All right, so keep that in mind. So we have this, and then what is the dimension of V? Well, let's just keep that as it is. And what is the dimension of nor T? Well, since T is invertible, right, then T is injective, which implies the nor T is just 0, which implies the dimension of nor T is equal to 0. Okay. Invertible means the injective and the surjective, right? And the injective, well, you only have one input goes to different output, right? So 0 goes to 0, you cannot have another one go to 0. So the nor T is only 0. And then that means the dimension of nor T is 0. And then what about the range T here, right? Remember, the range T actually is a subspace in W, all right? So since T is invertible, then the dimension, T is surjective. So that tells us the range of T will be everything in W, right? Because surjective means every W there, you are able to find a V. All right. So if you have the T of V, that will cover every W in your W space. So the range of T will be equal to W. So this implies the dimension of the range of T is equal to the dimension of W. All right. So then, all right, the fundamental theorem becomes this. So dimension of V, we keep it here. Dimension of nor T is 0. Dimension of the range is the dimension of W. So that tells us the dimension of V is equal to the dimension of W. So we proved one direction of this theorem, right? We said, well, we proved isomorphic if and only if the dimension is the same. Now we know isomorphic, yes, we proved the dimension is the same. And now let's prove the other direction. There's still the finite dimensional subspaces. So let's assume, right, the dimension of V is equal to the dimension of W, which, let's see if the book uses any know something there. Dimension of V. So let's put n here, all right, because they use n here, dimension of n here. All right. So then we're going to let V1 up to Vn, this be a basis. All right. So we want to, in this case, we want to prove, all right, so the V and the W, they are isomorphic. All right, so let V1 up to Vn be a basis of V, and the W1 up to Wn, this is a basis of W. Okay, and to prove this is isomorphic, V is isomorphic to W, we need to find a linear map T from V to W, and this T is invertible. All right, so we're going to define the T, which is from V to W, by this way. We have a T of any, because any V can be written as a linear combination of the bases, and then we just say, well, the V1 is corresponding to W1, V2 is corresponding to W2, Vn is corresponding to Wn. So then we carry the same scalars and then make it W. I think we actually said this idea before. All right, define this. All right, then all right, check T is linear. That's everyone can check this. All right, so it's not very hard to check. I'll leave this as an exercise. All right, and then T is injective. All right, and T is surjective. All right, so let's left this as exercises. All right, make sure you verify this. All right, do not take what I said for granted. Do not take what the book said for granted. Or always convince yourself actually those statements making sense. All right. Right. So for instance, what is linear, right? That means if you have a V1, V2, well, we probably don't want to use V1. Right? If you have U1 in V, U2 in V, you add them together. Do you have T of U1 plus U2 equal to T of U1, then plus the T of U2, right? And if you have A times U, T of AU is A times TU. Do we have this, right? And injective, right? Injective means, well, different ways to do that, right? The easiest way to do that is just to show if you have the T of something equal to 0, then that thing must be equal to 0. Right, so can you do that? That's probably not very hard, right? Because if you have T of something V equal to 0, well, then that means all this A1, W1, A2, W2, A and Wn equal to 0. But the W are linearly independent. They are bases. So A equal to 0. All this A equal to 0 give you the original V equal to 0, right? We saw that idea before. And the surjective, right, that's even easier, right? Because if you have any W there, then that means the W can be expressed by those bases in W1 to Wn, right? And then the V to give back to V, so you construct V, right? So those, anyway, so if you can show those, then this implies, right, T is invertible, and T belongs to the LVW. So this tells us the V and the W, they are isomorphic to each other. All right, so that proves the other direction of that theorem. All right, so with this theorem, then now we are able to study something relatively simpler finite dimensional vector spaces, and then use that to say something about the more advanced vector spaces. And for today, what we're going to do is we're going to say, well, we know those matrices we talked before, the m by n matrices. And then if you collect all those m by n matrices together, that's easily to see that's a finite dimensional vector space, right? So because each basis is a matrix, all entries are 0, just one entry is 1, right? You just keep one from the maybe the at 1, 1 position, at 1, 2 position, and so on, and then put all this equal to 0. So there in totally you can do like a m by n such matrices, and altogether they form a basis to this matrix vector space. And then we're trying to say is, well, then that vector space is actually isomorphic to the vector space LV to W. All the linear maps from the V to W together with the addition and the scalar multiplication, they form a vector space. And these two vector spaces, they are the the LVW and then the matrices vector space, they're isomorphic. Well, how many dimensions, what is the dimension of the matrix one? Well, that's m times n. So therefore, we know the dimension of the LVW is also m times n. All right, so that's what we're trying to accomplish next. So before that, let's kind of quickly recall how we actually define that matrix. All right, so let's recall something we did before, right? So if you have a vector space V, finite dimensional, so you have the basis, all right, and then you have a W, a T, or from this to W, and the W is W1 to Wm, all right. Then we defined, or if you recall before, what we defined is the M, we said T, and then the basis, and then the other W basis, right? So if you recall how we define this, right? So this is defined by the each entry. And how do we define the each entry, right? So we define this. We said, well, let's look at the T acting on any V sub j, V1, V2, Vn, right? V sub k here, right? And then this is, well, when T will take that to a vector in W, right? So any vector in W can be written as a linear combination of W1, W2 up to Wm. So what we're saying is, well, this is your A 1k, and then plus A some 2k, and then plus A some mk here. All right, I'll remember the sigma notation we used before. Or you could have something like try to see what the subject they use, I or j or they use j here, right? So jk, right? So the w j here, right? J from 1 to m. So that's our definition where those a come from, right? So then this m here, right, is basically this a11 up to a1n, and then we have the am1 up to amn, right? So that's how we define this. All right. So because we're going to use this, so then, well, with this definition here, all right, that leads us to our next proposition saying, all right, this kind of map, because you have you fix the v and the w, right? The v and the w, they are arbitrary, but they fixed, right? And then, so every time there is a linear map T there between this v and the w, then there is such a matrix, because you pick up a basis in v, pick up a basis in w, right? And then you have this T given, then that's all three together going to give you a matrix, right? And then there is another T, all right? So you get another matrix. So then this correspondence given a T and in the L from V to W and given a matrix, then this correspondence, is that a linear map? And is that well, the linear part, I think we probably already proved that before, right? But is that an invertible map, right? If the answer is yes, then that's going to allow us to establish this kind of isomorphism we want between these two vector spaces. All right, so that's what the next proposition is trying to tell us. So what we're trying to say is, all right, so this is the next proposition is, suppose that, all right, so V1 up to Vn, so this is a basis of V, all right, and W1 up to Wn is a basis of W, right? Then this map, right, M, right, is an invertible map between LVW and this MAT, all the matrices collect all together, M and F, right? So these are all the M rows and columns matrices defined over this field, either the R or the C, right, of the that's what generally speaking we call the F. All right, we call the F. All right. So then let's prove this one here, all right? And then once we have that, we'll be able to accomplish the last thing we want. So here is the proof. All right. So let's begin by showing this map is injective. All right. So in other words, what this so this is the make it clear. So this one is the matrix. All right. This one is the matrix, and the map we are saying. All right, so this is the matrix, but the map we're seeing, this is from the LVW to this all the collection of this M by N matrices, and this map is defined in the fashion is if there is a T. Okay, so your input is a linear map. That's your input, and then this map M will take this capital M is a map between this L space and this MAT space. So that will take the T is an element in L. This M will take this element to a matrix on the other side, and then this matrix is just this one. Right? And then the entries of this matrix is defined by this T V sub k. Is this you write this T of V sub k as a linear combination of W, and then this V j k is the kth column. That is how you form each column, right? TV1, this linear combination of use W to express TV1 will give you the first column. This linear combination use W to express TV sub 2 give you the second column, and so on. Right? So you fix these two vector spaces, the basis, and then you say, well, I got one T. Well, then one T going to give you one matrix. Another T going to give you another matrix. So this is the correspondence. The input is the T, and then that is sent to a matrix W here, or the M here, right? So then we're saying this is injective, right? What means this is injective? In other words, what we want to show is we need to show this, to show that if M of T equal to 0, then T is equal to 0. All right? And here we put like two zeros here, but to be very clear, you really need to understand the definition of this this transformation M here. Let me just call this transformation. All right. So then this is a M by N matrix. All right. Because your M take a linear map, transform that to a matrix. All right. And then this 0 is the 0 map from V to W. All right. So in other words, this 0 belonging to this MAT, MNF, and then this 0 belonging to the L, VW. Or sometimes since notations are really similar, or we may not think this carefully, but that's the meaning of each 0, right? So why this matrix equal to 0 will lead to you to see that the map must be 0? Well, the reason is, remember, by the definition of this MT, V1, Vn, W1, and Wm, right? So by this definition, right, how did we actually form that matrix when you pick up a linear map T, right? So your thing is this T of V sub k is the sigma, this is j from 1 to k is from n, right? So j is from 1 to m, and then this ajk, and then we have this w sub j here, right? So then if this matrix is equal to 0, that implies all this ajk equal to 0 for any j between 1 and m, and for any k between 1 and n. So then this implies the TV sub k is equal to 0, because all this A are 0. Because your thing is the TV1 is the linear combination of W1 up to Wm associated with the A11, A21, A2, A31, and AM1, right? Use the first column, that's your weights in front of each W. Well, all those weights are 0. So when you make the linear combination, you get TV1 is 0, and similarly TV2 is 0. All right? So all this is equal to 0. But if you have a linear map acting on all the basis vectors give you 0, then that tells you the T of V, because any V is a linear combination, right, of those V sub k. So if T of V sub k is equal to 0, then this tells you the T of any V is equal to 0. And then this just tells us T itself is just a 0 function, or 0 map from V to W. All right? So that's what we want to prove. And then this proved the M is injective. So this is really, I think, when we come to this point, you really have to think about all the meanings of the notations. You have to be very clear thoughts about what we talk about for all those things we've written down. So that's important. And then what else to left? So we still need to show this M from LVW to this matrix M and Fi. So this is surjective. So in other words, we for any matrix, for any matrix, what is the, I'm trying to say, okay, A here, I think not U there. So for any matrix belonging to this matrix vector space, there exists a T in LVW such that the M of T is equal to this matrix. In other words, we want to prove this. We want to prove for any of this. So let's consider a matrix A here. So actually this direction is not that bad if you understand the definition. So we have the A11 up to A1n, AM1 up to AMn. So we're just going to define, given the A here, we're going to define a T such that T of V1 is just this A11 times W1 or A21 times W2, and then AM1 times WM or TV2 is the same as A21W1, A22W2, or AM2WM. So generally speaking, we have the T any V sub K is so this is the 2, 1, 2, 2. Yeah, so this is the in the case column. So this will be first row. This is 1, 2. 1, 2. So this is 1K times V1, 2K times W2, and then MK times WM, and then the last, so this for any K, and then of course if you have T V sub N, so this is the A, if you go to the last one, this is the 1N V1, and then 2N W2, and then MN WM, So basically to define an operator, we define how the T behaves on the vectors in the basis. So you define T such as this. And then for any, of course, for any other V, well, that's a linear combination, So then you can, put the weights in front and then put it like maybe something like if V is a C1 V1 plus C2 V2, then you have the T of that is T of C1 times TV1 or C times TV2 and so on. So then you can extend this to any V here. So then check that this T is linear. So left this, I can verify that it's a linear one. And then what else? Well, if you know this is linear, then what we're looking for, We're looking for this T, the matrix representation of T is the same as A there, But by the definition of T, the matrix of this T and under this basis, so this our definition, right? So what you mean you want to represent this by a matrix? Well, you represent it by this matrix because you want to write the TV1 as a linear combination of the W, right? But if you look at the way we define the T, well, the TV1 is using those first column of A, right? Of the A11, A21, and so on. So then when you follow the definition, write this matrix representation for T, then that A11, A21, A31, this will be in the first column of your M, T, right? And then similarly, the second column of A will be still in the second column. So then just by the definition, this is exactly the same as the A here. All right, so in other words, our thought is, hey, here's the matrix A there. Using this matrix, how you're going to construct a linear map? Well, then this matrix multiplication matrix, use the first column, makes the combination of the W, give you the TV1, and so on. So this is a linear map, and that linear map is exactly the coefficients is exactly the matrix coefficients. So when you represent this linear map into a matrix, that matrix is unchanged. All right, so that's what we're saying. So therefore, the T is surjective. All right, so since we found the T, which is linear, or actually I still need to check this linear, all right, and the T is invertible, thus, right, this V is isomorphic to W. All right, so this is the major theorem, one of the major ones we proved. And once we have this thing, then we are able to see the next proposition, which is very naturally get from here is if U and W are finite dimensional, then this LVW is finite dimensional, and actually let me write on the same page, the dimension of this vector space, we proved earlier this is a vector space, this is dimension V times dimension W, and each is a number, right? And why we have that? Well, because this LVW is corresponding to this matrix subspace, vector space, this MAT space, right? But that is M rows and columns, so that in total you need like this M by N matrices to make a basis. So the dimension of that mat space is M by N, and so that is equal to the dimension of the L space. But then M by N is M is the dimension of the W, N is the dimension of V. So you multiply this, that's equal to M times N. All right, so that's actually interesting property here, right? Because if you think about, for example, if you think about what is if the L from like R3 to R2 here, right? Then the dimension of this one, right? For all the linear maps from R3 to R2, then this is just equal to 3 times 2 is equal to 6. All right. So then that's how we use this. And then if you have, for instance, the dimension, if you have something from a polynomial space to a polynomial space, let's say if you have something from a P sub 3 of R, right, to a P of R here, well, then the P sub 3 of R, you need 1, you need X, you need X squared, you need X cubed to span that. So then that will be 4, right? And then the P of R, which is just either the constants or the linear terms, well, then you just need a constant and X. So there are 2. So all the linear maps over this together, so the dimension is 8. All right. So in other words, all the linear maps over these two subspaces can be represented by a basis containing 8 of such linear maps. That's a very interesting result. All right. So for the last part, we'll quickly prove the last theorem in this section, which is not very hard. We just focus on, I know this recording is a little bit longer, but hopefully the last part will be more straightforward. So this theorem says, what if we do not have the LV to W? What if the V and the W, they are the same, right? That becomes the operators, right? We said L of V is a collection of all the linear operators. So then suppose that V is finite dimensional. All right. So if T is belonging to LV, then the following are equivalent. So there are three things. The strongest requirement is T is invertible, right? This means T is injective and surjective. But we're saying if your T is just defined on V to V, then invertible actually is equivalent to T is injective and equivalent to T is surjective. Okay, so these are the three things are equivalent. All right. So in other words, if you know any one of them, the other two automatically also true. Right. This is actually convenient for us. But I want everyone to think about what you have learned in your linear algebra, or think about the square matrices, right? So when you're doing the square matrices, there are a lot of ways to characterize that a square matrix is invertible, right? That's what we care about. And well, of course, one thing is to show invertible it's indeed invertible, but also you could say, well, if I have AX equal to 0, if the only solution is 0, then that also enough to show this actually is invertible. Or if I have AX equal to B, right, if for any B there is a solution, that's also enough to show this matrix A is invertible. All right, so there's a very similar results using the linear algebra. We, of course, that time we only focus on the matrices, but really this is just the abstract version for that. And it should not be surprising because we just said, those spaces are isomorphism, right? So the LV there, because the V and the W are the same, so then that means your representing matrices are just square matrices. So all the matrices properties for the squares happening here, and all the T in the operators in LV also can be find the counterpart theorems for the matrices. All right, so very similar results. So when we prove this, it's really A to B, there's nothing to say, right? This is obvious because the invertible means it's injective and surjective, right? So that's automatically give you the B, assuming the A. And then for the B to the C, well, we have to use this fundamental theorem again, right? So we can see this is really, really useful. It's the dimension of the V is the dimension of the null space and plus the dimension of the range, right? And then, well, since T is, our assumption is T is injective, then what we get is the dimension of null T is equal to 0. So this implies the dimension of the V is the dimension of the range of T, right? But remember, the T is from V to V. So this time you can think of the V is that W before, right? Is the codomain there. And so if the range is actually dimension of the range is equal to, because the dimension of the range is the range T is a subspace of V, right? So this together tells you actually the range T in this case with additional information, the dimensions equal to the entire vector space, they equal to each other, right? So I guess the question is why? All right. So the way to think about this is something we learned much earlier, probably in chapter 2, right? So you said, well, if there's a subspace, it's a finite dimensional, so then you can have a basis for the range of T, right? But the number of the vectors in the basis by this condition is equal to the number of the vectors in the basis of V. So if you want to extend the basis of range T into a basis of V, nothing you can add there because the dimension is the same. Well, then that tells you actually this basis is also the basis of range T is also basis of V. So then that tells you the two, the subspace becomes the entire space, vector space. All right. So that's the reason I add those details to that question mark there. And the C implies A is, we know this is surjective. We're trying to show this is also injective, and then that's of course invertible, right? So assume T is surjective, then right the dimension of the range of T is equal to the dimension of V. So then this fundamental theorem, dimension of V equal to dimension of nor T plus dimension of range T. So first, this is equivalent to the dimension of nor T is the dimension V minus the dimension range of T. But these two conditions together tells us the dimension of nor T is equal to 0 because T is surjective means the range and the V is the same. All right, and then they have the same dimension, so the difference is equal to 0. So nor T is equal to 0. So this tells us T is actually injective. All right, so since T is also surjective, then T is invertible. All right, therefore, assuming the B part, we proved the A part. All right, so this is really, I think, a very convenient equivalence conditions for us, right? Because in order to prove the T is invertible, we can release the requirement from requiring both surjective and injective to any of these two holds, then the other property also automatically holds. All right. So, but that's only from the L from the V to the V. If that's from the V to the W, if there are two different sub-vector spaces, then we do not have this congruent. All right. Keep that in mind. All right. So I'm sorry about this long recording, or it seems like naturally to finish this. But the good news is, well, now we're finished the section 3D, or most of the sections we want to cover in section 3D. We finished that, so just left with the quotient space for the next section. So far, I think the class has got into the area where there are a lot of proofs, and many proofs need to make the connections with the past propositions or the theorems. So make sure stay the pace of the class, and then read the book carefully, read my notes, and then watch the recordings, do whatever you can. But a solid understanding is a good way to keep you in a good progress in this class. All right, so see you in the next recording. Thank you.